Okay, thank you for the introduction, and I'd like to thank the organizers for giving me this opportunity to talk. So today I'm going to talk about my motivation of my recent study and report result based on the joint work with Shinji Koshida. Yeah. Okay, I will divide my talk into 4 parts. In the first section, I will explain the background of my main result of about the Velind formula. And then in the second section, I will I will explain a little bit non-standard Velind formula for the affine vertex operator algebra at Katsuaki model admissible levels. Then we move on to our main result, and the precise statement of our main result is given at the end of the third section. And in the last section, I will explain the outline of our proof. And also, I'd like to discuss another proof of our main result by using induction functors. Okay, so let's first recall some notations and the notion of affine vertex algebra. We write G for a finite dimensional Lie algebra over the complex number fields, and we write for kappa for non-degenerate symmetric invariant binomial form on the Lie algebra G. Then it is very well known that the corresponding affinization G hat is defined by the one-dimensional central extension of the roof Lie algebra, and the corresponding vacuum representation we write VG kappa like this, and then this representation has a structure of vertex algebra. Then we can consider the notion of the modules over the vertex algebra. Then the category of weak modules over the affine vertex algebra can be identified with the full subcategory of the category of affine Lie algebra of the corresponding levels. These results are very basic. Then when G is simple or a virion case, and we assume that the corresponding non-degenerate form kappa is non-critical, that is, the kappa is L times the normalized invariant form, and here L stands for the level, and L is not equal to minus H check. H check here is defined by the dual coset number of the simple Lie algebra G, or if G is a virion case, H check is defined as 0. Okay, in that case, we can use the Sugawara construction, and such construction gives a VOA structure on the affine VOA, and we use these notations, and we also consider its unique simple quotient, and we use this notation. Okay. Then when G is a virion case, we simply write pi G for the corresponding affine VOA, which is known as the Heisenberg VOA. Okay. Then our VOA is set to be regular if every weak module decomposes into a direct sum of irreducible ordinary modules. Then, in 1999 paper by Haishen Li, every regular VOA is proved to be C2 cofinite. Here, the C2 cofinite condition is a certain finiteness condition for the VOA, and the very important consequence of the C2 cofiniteness is the corresponding VOA has only finitely many irreducible modules. Okay. Then by the result Don Lee Mason in 1997 paper, and together with Don Mason's paper in 2006, if G is a simple real algebra, then the corresponding simple affine VOA is regular if and only if the corresponding level is non-negative integer. Okay, this is very standard results on the regularity of the simple affine VOA. Then our main object in this talk is bearing the formula. So for a given regular VOA of strong CFT type, yeah, today I do not discuss about the detail of this assumption. For example, this is just a condition for the self-duality, and together with the non-negative L0 eigenvalues and the uniqueness of the vacuum. Okay, anyway, in that case, there is a very non-trivial connection between the modular S matrix and the corresponding fusion rules, which is known as the variant formula. And the modular S matrix is defined as the presentation matrix of S matrix in the modular group SO2Z with respect to the irreducible trace functions. So the definition of the modular S matrix is based on the modular invariant property of the space of trace functions. Okay. On the other hand, the fusion rule is defined as the dimension of the space of intertwining operators between irreducible modules. Okay, so this definition of the fusion rule is written in terms of vertex algebra language. So in the vertex algebra language, this variant formula is proved by Huang in 2008 paper. Okay, then the importance of the variant formula is due to this fact that the modular S matrix is relatively easy to compute than the fusion rules. So we can compute fusion rules by using the modular S matrix. This is very important and a very useful theorem in the representation theory of regular VOA. Then, very roughly speaking, Moore and Zyberg figured out that the notion of modular tensor category encodes the important structure, the variant formula, and other properties in the purely categorical language. So the theorem by Huang in 2008 says that the category of modules over the regular VOA of strong CFT type carries a natural modular tensor category structure based on the theory of vertex tensor category developed by Huang and Rabowski. So this modular tensor category is also deeply related to the small quantum groups at roots of unity. So this is very deep fact, but today we only consider the vertex algebra side. Okay, so let's move on to the Katzbach-Model admissible level cases. Okay, so so far we considered only regular cases, but at the admissible level, the corresponding affine VOA is not regular, and they have infinitely many irreducible weak modules. So there are so many modules, and so the situation is very different from the regular cases. However, they include only finitely many irreducible highest weight modules for the corresponding affine VOA, whose character functions span an SO2Z invariant space. So in some sense, this non-regular VOA has some nice modular invariant property. So the naive question is, the varying formula still holds in this case or not? Okay. So this phenomena is firstly found by Kazama-Suzuki. So we call these levels Kazama-Suzuki admissible levels. Okay. Okay. So let L be an affine VOA, a simple affine VOA at an admissible level. Okay. In that case, so there are some supporting evidence for the generalization of Leyland formula. The first one is the theorem by Awakawa, proved in 2016, says that the category O tilde of weak L modules in the VZZ category for the corresponding affine Kac-Moody algebra is finite. I mean, there are only finitely many irreducible objects and also semi-simple. Okay, so the whole weak module category is very big and difficult, but if we consider the highest weight module category, there are only finitely many irreducible modules and there are no non-trivial extensions. Then by using this semi-simple results, in 2019, Krotik proved that if the Lie algebra G is simply laced and we impose some assumption on the admissible level L, then the full subcategory of O tilde, if we write OLZ here, has a modular tensor category structure. So the objects in the smaller category are G integrable, all G integrable. So the objects in the smaller category have finite dimensional L0 eigenspace decompositions. Okay, so the objects in the smaller category are all ordinary module. Okay, so in that case, the smaller category has a structural modular tensor category, so we get the corresponding variant formula in the smaller category. Okay. But Kazama-Suzuki already proved that the modular invariance property holds for the larger category O tilde case, but which is not proved to have a tensor structure if the level is not regular cases, so genuine admissible cases. So the long-standing problem, very difficult problem is, how can we construct a vertex tensor category, say C, the category C, appropriate weak modules for the admissible affine VOA, which contains O tilde as a full subcategory and equipped with the Leyland formula with suitable modifications. So this is my motivation of this result. So I'd like to discuss this kind of generalization of Leyland formula beyond the regular cases. Okay. So there's a known potential candidate for the category C. So here let CLG be the category of weight L modules with respect to a Carlton subalgebra of G. So the precise definition of weight modules are given in the third section. So in that case, so if we consider the appropriate weight module category, then readout proved that a version of the Leyland formula holds in the level.
I can't hear you for some reason. I don't know if it's just me.
Mm-hmm.
I can hear you now. Yes.
Okay. Okay. So let's continue. Okay, so in the theorem 2.3, Ryo proved that version the Rayleigh formula holds in the if the level is -1/2 and G is SO2 case. So in this specific case, the variant formula is actually the variant formula actually holds in some sense. Then also Krotik Ryo proved that conjectural variant formula for the general admissible level for the SO2 case predicts consistent fusion rules, namely the corresponding Welland formula predicts the symmetric and associative and non-negative integer fusion rules. Okay, this is a very strong consistency check, and we can expect this kind of variant formula would hold in this category, but the corresponding proof is not hasn't been yet given. So the reason is there are some difficulties at admissible levels. So when we consider the admissible level L, which is not equal to non-negative integers, then we of course have these inclusions. So the smaller category O is included in the larger category O tilde, and our potential candidate C includes all the categories. But there are differences between them, and the largest categories in C has uncountably many typical modules and atypical irreducible modules. So there are two types of irreducible modules. The one is called typical, and the other is called atypical. So anyway, there are uncountably many irreducible in the largest category C, and in particular, so especially typical characters are not functions, but distributions. So the typical characters do not converge at any regions. And also the result in Ryo's original paper is based on another approach other than the vertex tensor category theory. So another approach to fusion rules given by Nam and Gabriel Kausch. So we need to check the equivalence between the NGK algorithm and the other side, vertex tensor category algorithm. So these there's a very nice exposition by Kanade Redout. So, but at this moment, we do not have the equivalence result between the vertex tensor approach and NGK approaches, to the best of my knowledge. Okay. So, okay. So this is my motivation of my recent study. So I would like to understand the generalization of the variant algebra, variant formula, and the admissible levels. Okay, so we now move on to the main construction, which is about the Kazama-Suzuki coset constructions. Okay, so here let G be a simple Ryo algebra, and the level is not critical. In that case, we first considered this kind of Fermionic construction of the level H check simple affine Ryo algebra, affine VOA. So this is a very standard result, and the statement is the adjoint action of G on the G itself induces a conformal embedding of the level L check affine VOA into the Clifford vertex operator superalgebra. So this means we can construct a level L check affine Lie algebra in terms of free fermions. Okay. So by using this construction, and we take a Cartan subalgebra H inside of the G, then we consider these kind of diagrams, so which says the upper delta means a diagonal embedding of the level L plus H check affine VOA inside the tensor product of level L and level H check. So one side is a simple quotient, but we can construct the corresponding diagonal map from the level H plus H check. Then we use the conformal embedding in the fermionic construction. Then we can embed the level L plus H check inside of the tensor product at level L and Clifford vertex operator superalgebra. And we consider the corresponding Heisenberg VOA, sub VOA inside of the level L plus H check affine VOA. Then the corresponding image of the Heisenberg VOA is included in this tensor product. So here the G over H means the orthogonal complement of H in G. Okay, so G over H has a natural non-degenerate invariant form, symmetric invariant form, so we can consider the corresponding Clifford VOSA. Okay, so by using this diagonal action, we can consider the corresponding coset vertex operator superalgebra like this. And also we can consider its unique simple quotient, and we write Ks upper script L is universal cases, and Ks subscript L stands for simple quotient cases. Okay, and these coset vertex operator superalgebras are known as the Kazama-Suzuki coset VOSAs, which admits an n equal 2 superconformal structure. So the modules for these coset VOSAs has natural action of the n equal 2 superconformal algebras. So these vertex operator superalgebra are first studied by Kazama-Suzuki in the context of the n equal 2 superconformal field series. Okay, and also these construction related to the relative semi-infinite value complex for this reductive pair of Lie algebras. Okay. Okay. Now we would like to consider the corresponding Cartan subalgebra for the affine and also the Kazama-Suzuki side. Okay. Since Cartan subalgebra of the tensor product of affine VOA and the Clifford VOSA has this length, so the length G means the dimension of the Cartan subalgebra of G, and the other side here, phi plus stands for the set of positive roots for G, and sharp stands for the number, the cardinal of this set. So this stands for the dimension of the Cartan subalgebra of this Clifford VOSA. And we consider the Heisenberg coset with respect to the diagonal action of the Cartan subalgebra of G. So the corresponding coset has this dimensional Cartan subalgebra, and we write HKS for the Cartan subalgebra of Kazama-Suzuki coset VOSA. Okay. Then we have natural isomorphism of VOSA between the Heisenberg cosets of the affine VOA, and the other side is Heisenberg cosets of the Kazama-Suzuki VOSA. Okay, this isomorphism is a very natural one, and this statement is very trivial because the Heisenberg cosets for the Clifford VOSA is trivial, so we can easily prove this isomorphisms. But the resulting Heisenberg coset is very interesting. For example, if we consider the L equal non-negative integer case by using the Heisenberg coset theory developed by Krotik, Kanade, Renshaw, and Redoubt, we can prove that the corresponding coset KSL is regular because the original affine VOA is regular. Then in the case of SO2, the corresponding Kazama-Suzuki coset VOSA is generated by only the n equal 2 superconformal algebra. And also this level corresponding to the unitary minimal series representation. So this corresponding VOSA is very well studied VOSA. Only has 4 generating fields, and the structure is very easy to study. But the corresponding Heisenberg cosets are a little bit non-trivial, and actually this isomorphism is proved by Arakawa, Lam, and Yamada, and the more general case is proved by Arakawa, Krotik, and Renshaw, and known under the name of level 1 duality. Okay, so the resulting Heisenberg coset is the principal W algebra of type A. So the corresponding Heisenberg cosets are a little bit non-trivial, and these two vertex algebra, affine vertex algebra and the Kazama-Suzuki coset VOSAs are both of them are certain, simple current extension of the tensor product of principal W algebra with Heisenberg vertex operator algebra. Okay. So this is a regular case, but we are interested in non-regular cases. Okay. So in the non-regular cases, the situation is very difficult, but we have inverse coset construction like this. So this is from my previous paper, and this says there exists a Heisenberg sub-VOA inside of the tensor product at Kazama-Suzuki VOSA together with non-negative lattice VOSA of this form. Okay. In that case, we can construct an explicit isomorphism between the original affine VOA to the Heisenberg coset of the tensor product of this form. Okay, so in some sense, this construction is inverse to the original Kazama-Suzuki construction. So, and we should remark that when G is equal to any SO2 case, this construction is originally given by Feigin, Semikhatov, and Tepnin. So I usually call this construction as Feigin, Semikhatov, Tepnin coset construction, or it's sometimes referred to as an inverse Kazama-Suzuki coset construction. Okay, so this is very this construction plays very important role in my talk. Okay, so far we obtained the following two constructions. One side is affine, from affine to Kazama-Suzuki, and the other side is from Kazama-Suzuki to affine side. Okay. But though the affine VOA and the Kazama-Suzuki VOA seem very different, so one side is VOA and the other side is VOA, so very different. But it turns out that their weight modules are quite similar. Their weight modules have very similar structures. So we'd like to consider weight modules for these VOA and VOA. Okay, so I would like to introduce the notion of weight modules. So let V be a conformal vertex superalgebra, and we consider the corresponding Heisenberg sub-VOA. I write pi A. Then pi A weight V module is defined as a weak V module, and which decomposes into a direct sum of the Heisenberg Fock modules for the corresponding Heisenberg sub-VOA. And we also assume that corresponding coefficient space, I write omega lambda of n, decomposes into finite dimensional generalized L0 eigenspaces. Okay, here pi A lambda stands for the corresponding Heisenberg Fock pi A modules. Okay, so this is the definition of weight modules for V. Then for weight modules n, and we pick certain weight lambda, then the coefficient space omega lambda can be naturally identified with the subspace of singular vectors with respect to the action of Heisenberg VOA, like this. So by taking such singular vector subspaces, we can define the functor from the original modules over the V to the corresponding Heisenberg coset modules. So this functor is referred to as a coset cohomology functor, because this functor can be written in terms of the Hom functor, and we can regard this functor as the zeroth cohomology functor. Okay, so by using this coset cohomology functor, we can prove that the two bidirectional coset cohomology functors establish weight-wise linear equivalences between the category of weight modules for affine side and the category of weight modules for the Kazama-Suzuki side. Okay, so this kind of construction is very standard, but we need the inverse construction for the Heisenberg coset for the precise proof of the equivalence. So the inverse construction plays a very important role in the proof of this equivalence. Okay, then we denote the former category, and I mean the affine side, by CLG, and the latter side, the Kazama-Suzuki side, DLG. Okay, so we have two categories of weight modules. Okay, now, so what is the advantage of the Kazama-Suzuki side? Our main problem is the affine side, but we consider now the Kazama-Suzuki side. So first, we recall that typical characters from the affine side do not converge and only define distributions. But on the other hand, all irreducible characters from the Kazama-Suzuki side do converge to meromorphic functions. So there are no divergence phenomena in the Kazama-Suzuki side. This is very different from the affine side. And since the computation of fusion rules in affine side can be reduced to that in the Kazama-Suzuki side, so we are now interested and whether the well-linked formula holds in the Kazama-Suzuki side or not. Okay, so the point is modular property in the Kazama-Suzuki side is better than the affine side. So this is why we care about the Kazama-Suzuki side. Okay, then we arrived at our main result. So the main result is all the fusion rules between irreducible objects. In the very specific case, the level is -1/2 and G is equal to SO2 case. And in that very specific case, we can prove that the corresponding modular S matrix actually computes the correct fusion rules by the Berlin formula. So in some sense, we have the Berlin formula in this category. But we should note that we only care about irreducible objects. So there are so many non-trivial extensions between irreducible objects. So we need to consider other non-trivial extensions. So at this moment, we only prove that the irreducible fusion rules are computed by the modular S matrix collectively. Okay, so the modular S matrix computation is done in my previous paper, and the joint work proved that their coincidence. One side is the Bernoulli formula, and the other side is actual fusion rules. Okay, so in the computation of the fusion rule, we use the oscillator representation of SF2 hat. So we regard SF2 as SP2. So this construction plays a very important role in our proof. And we also expect that our result can be extended to the higher rank symplectic cases. So after this, I'd like to explain how to prove this result and how to compute the fusion rules. Okay, and also we'd like to mention the more general conjecture, the same within the formula, also true for general admissible level L and general G, simply algebra G. And if the G is equal to SL2 case, the paper by Kortik, Liu, and Ritter and Wood computes the same representation theory, the Kazama-Suzuki side, and they use the induction factor, actually they also compute the corresponding fusion rules by using the corresponding fusion rule in the affine side. So we'd like to compare our results with their results. And actually we give some comments at the end of this talk in this direction. Okay, so this is our main results. Okay. Are there any questions? Okay. Is it clear so far? Okay, so we move on to the outline of our proof of the main results. Okay, so we use oscillator representation of symplectic Lie algebra. So we recall the definition of symplectic Lie algebra. So we pick the standard basis to n-dimensional vector space like this. Then the symplectic Lie algebra is defined by this matrix J. So J square is equal to minus identity matrix. Then the corresponding, this invariant relation defines the symplectic Lie algebra. Then there's some nice basis for this Lie algebra. Then we get a nice basis of symplectic Lie algebra, which decomposes into the GLN, and these two modules for GLN as one side is the degree 2 symmetric tensor for the natural representation of GLN, and the other side is the corresponding dual modules. So symplectic Lie algebra decomposes into the direct sum of adjoint GLN representation and these two representations for the GLN as a Lie subalgebra. So X correspond to the GLN part, and Y and Z correspond to the two degree 2 symmetric tensors for this GLN subalgebra. Okay. So if we use these nice base of symplectic Lie algebra, then we get the corresponding differential operator realization of symplectic Lie algebra. So this construction is known as oscillator representation or value representation or Segal shell value representation, or maybe metapractic representation. Okay, let Wn be the rank and while algebra generated by the differential operator Pi and the multiplication operator Qi. Here I is one runs through 1 to n. Then there exists a unique algebra homomorphism from the symplectic Lie algebra into the Weil algebra, like this. So as I mentioned earlier, the X part corresponds to the GLN part. So the X part realize the differential operator realization of GLN. And we also have two module part for GLN. But the one side is written in terms of degree 2 differential operators, and the other side given by the degree 1 differential operator. Actually, this is just a multiplication operation. So this realization is not homogeneous with respect to the natural grading of the Weil algebra, but this construction corresponds to the unitary representation of the real symplectic Lie algebra. Okay, so this is very classical construction of the symplectic Lie algebra. Then we'd like to generalize this construction to the affine case. So actually, the corresponding result is due to Feingold and Frankel in 1985, I think. So in this talk, we give the corresponding result in the language of vertex algebra. Okay, let Kali Wn be the rank and while VOA of central charge corresponding central charge is -n. Okay, then there exists a corresponding unique VOA homomorphism from the simple affine VOA of level 1 minus one half of symplectic Lie algebra inside of the rank and while VOA. And the morphism actually corresponds to the original finite dimensional cases. Then we get the realization of the affine VOA at admissible level. Actually, this level corresponds to the admissible level for symplectic Lie algebra. Okay. So this is outline of our proof. Yeah, unfortunately, we need to restrict ourselves to the smallest case. Yeah, later I will give some comments the obstruction of the higher cases. Anyway, if we consider the smallest line cases, we write Ks for the Kazama-Suzuki VOSA and WC for the tensor product of Y VOA and Clifford VOSA. Then, by using the equivalence between affine and K Kazama-Suzuki modules, we can get the corresponding character formula for weight modules for Kazama-Suzuki side. Then we can see that the corresponding atypical modules have the atypical character which are written in terms of the so-called upper large sum. So upper large sum is known as mock modular forms, and their modular behavior is well studied. For example, in the paper by Semikato, Taormina, Tipnin, and other papers. So we can compute the corresponding modular transformation property of atypical characters. And also typical character actually converge to meromorphic function. And the corresponding modular transformation is relatively very easy than atypical cases. And together with atypical modular transformation property, we can compute the corresponding modular S matrix for the corresponding Kazama-Suzuki VOSA. Actually, the computation works for arbitrary admissible level for SL2. But the higher cases, we need to consider the higher rank upper large sum. So at this moment, we do not have the answer for the corresponding modular S matrix. Okay, and the fusion rule side. So this is done by the joint work with Shinji Koshida. And we need the two estimation, one from the estimation from above. We use the Frankel-Jubai module. So by using the categorical equivalence between affine side and Kazama-Suzuki side, we can construct a BZZ type resolution for the Kazama-Suzuki modules. Then we use such kind of resolution. We can compute the corresponding singular vectors and the corresponding maximal submodule structure. Then we can get the corresponding, we can compute the corresponding Frankel-Jubai module. Then we get the estimate from above of the, estimate of the fusion rule from above. And also the estimation from below, we use the very easy fusion rules for the tensor product of Weil VOA and Clifford VOA. So the fusion rule for this free field VOSA is relatively easy, so we can get the fusion rules for this free field VOSA easily. So by combining these results, we get the corresponding fusion rule result. Then we confirm that these two results actually coincide with each other. So this is our main result. Okay. So the problem is, if we would like to generalize this result to the higher line cases, so the most difficult part is the Frankel-Jubai module part, because the higher line case, the computation of Frankel-Jubai modules is very difficult. So we need another approach to this part. Okay, so for this part, we can use a certain relationship between the Kazama-Suzuki VOSA and singlet VOA. Okay, the singlet VOA MP is defined by the joint kernel of these screening operators. So here alpha generates a rank 1 lattice, and which the form is given by this, written in terms of P. Then yeah, so actually the first part of the definition is just the triplet VOA, which is very famous one. And we consider the subalgebra of triplet, which is known as the singlet VOA. And if we consider the P equal 2 case, which is appear as the Heisenberg coset as our cases. That is, the corresponding Heisenberg VOA for this Kazama-Suzuki VOA is actually the tensor product of the singlet VOA, n-fold tensor product of singlet VOA. And also we mentioned that the singlet VOA, in the case of P equal to 2, is isomorphic to this principle, simple principle W algebra. So this level is not non-degenerate. So the corresponding principle W algebra is not C2 cofinite. Okay, so singlet W VOA is not C2 cofinite. Okay, so the corresponding representation theory is very difficult, but if we compute and prove that the representation theory of singlet VOA has vertex tensor category structure in the in the most general cases, then we can use the induction factor from the tensor product of singlet with Heisenberg to get the corresponding Kazama-Suzuki VOSA. So the singlet, the representation theory of singlet VOA is very important for the generalization of our results. Okay. Okay. So that's all for today. So there are some future directions of this result. The first thing is generalization to the OSP cases. So there's a corresponding oscillator representation for OSP cases. So the OSP cases is the interpolation of the spinel representation and metaprolectic representation. Anyway, there's a notion of the oscillator representation for OSP. So maybe we can generalize this kind of construction to the OSP cases at very specific level. And the second one is, as I mentioned earlier, the corresponding vertex tensor category structure for the singlet VOA is very important, and the corresponding Berlin formula is studied by Krotik and Mills, and they are very important in the generalization. And the third part is other types. We can consider the corresponding minimal representation, which is the corresponding associated varieties are the closure lies in the closure at minimal nilpotent orbits. So we'd like to consider the other type cases. So they may be very interesting. So we can consider these future directions. Okay, that's all for today. Thank you.
Thank you, Ryo. Let's just clap for Ryo.
Thank you.
Thank you so much. So I'm going to stop recording. Please, if you have questions for Ryo, go ahead and unmute yourself and go for it.